Welcome everybody to the last day of our AFLOW school. Today we will have two big topics, two very hot topics. One is phonons that we will talk about this morning. I will start talking about phonons in the harmonic approximation, and then Dr. Andris Moyanyuk will follow up with that with a quasi-harmonic approximation. And later this afternoon, Dr. Corey Osis will talk about how AFLOW can model disordered systems, specifically substitutionally disordered systems. Something else I would like to mention from a logistic point of view, we will send out a survey to all participants during lunch break that we would like to ask you to fill out about this AFLOW school. Is very important for us to report to NSF how you like the AFLOW school, how everything went technically, and we'll send you a survey during lunch, or for some people, dinner break. So we really appreciate if you could fill this out. And without further ado, I will start with lattice dynamics and phonons. So for those of you who are not familiar at all with phonons, I added to the PDF some textbooks on phonons if you at the end are interested in learning more about those. So they're also in your PDF. If you're interested, they're all very good books. But a quick description of what phonons are. Phonons describe vibrational motions of atoms on a lattice, and that's why they're shortly often referred to as lattice vibrations. So they're a collective property, and that's very different to what we have been discussing in all these sections before. We have only looked at a certain unit cell and calculated properties with respect to that unit cell, but phonons extend to the entire crystal. That has some very important consequences for the calculations that we're going to do. They're responsible for a lot of important physical properties, mostly transport properties, thermal properties like thermal conductivity, heat capacity. They also play a huge role in electrical conductivity, thermal electricity, and superconductivity, and they can also determine and have a very important influence on phase stability. So let's look at actual lattice vibrations in action. We have, each atom has 3 degrees of freedom, can move in the X, Y, or Z direction. And if we just have one atom in a unit cell, we have essentially 3 different ways they can move. 2 of them are transversal. So if we imagine that we have a propagation direction in along this axis here that I'm highlighting with a laser pointer, there's 2 ways that the atoms can oscillate perpendicular to that direction. One is here up and down, the other one would go outside and into the paper plane here. And there's one way they can move alongside that propagation direction here. It's called, this is called longitudinal phonon, and the other one is called a transversal phonon. And each of these oscillations has a certain periodicity. We can see this one has a periodicity of 2 unit cells, 1 and 2. And this is the corresponding wavelength that's twice the lattice parameter here, and the corresponding wave vector is this vector here along the x-axis here. This wave vector Q will be very important when we talk about the actual atomic displacements. Now let's go to a diatomic basis. Now we have a different scenario. We have a total of 6 ways how these atoms can oscillate. Here looking at a long wavelength, which means we have a very small Q vector. We can have here a transversal motion where everything is oscillating in phase. And of those we have also 2 modes. They can also do the same thing into and out of the plane. And we can have the same thing longitudinal. Here they're all oscillating in phase with each other. And these are called acoustic phonons because they behave kind of like an acoustic wave. The other option is that they can oscillate out of phase. Here we see they're oscillating completely out of phase, opposite to each other. we have this transversal motion. And these are called optical phonons because they're often excited using optical wavelengths. And they also behave kind of like an optical wave instead of an acoustic wave. And here we have the longitudinal, where we have the out of phase oscillation, but the oscillation itself goes along the propagation direction here of the wave vector. But that is a short visual representation of how a phonon may look like. But how do we quantify this? To quantify this, we have to first introduce a little bit of notation. We're going to talk about supercells. A supercell is essentially an identical replication of the unit cell. This here will be a supercell. The entire thing will be a supercell of that unit cell, that shaded gray in the middle. And you'll see in the next slides a couple of indices that is decomposed into the atomic index inside the unit cell and a supercell index. If we are in the cell itself, we will just refer to that supercell index L as 0. And if we want to talk about an atom that is in a supercell, we give it the supercell index L. This is the common notation in phonon literature, so good to keep in mind when you actually read something about phonons. XL in the future will refer to anything that is just referring to the origin of the supercell. So connecting from the origin to another origin of the supercell will not get the kappa index. Here's another example to a different atom here in orange. And here is the origin. Here's the connecting vector to the origin of the next supercell. How do we quantify this? I will not use too much math here because it's very hard to follow a presentation with math, but just to give you a little bit of an overview of where we start. When we start with a potential energy here and we just expand it within a series, we get to this phi none term. And now we look at these kind of expansions when we displace an atom, which is what a phonon does. It displaces atoms from its equilibrium position. We essentially just use the series expansion, and we stop counting after this quadratic term here. And we are looking at the terms, these individual phi terms. Phi here is the first derivative of the potential energy with respect to a displacement in equilibrium conditions, which is the negative of the force that acts on this atom in equilibrium conditions. And in equilibrium conditions, all the forces should be 0, because otherwise you have a total force on the crystal and the crystal will fall apart, which is not equilibrium. So this term here will be 0, which is great. It's always great when a term adds up, subtracts out to 0. This here, this phi alpha beta L kappa L prime kappa prime is the second derivative in equilibrium position, in equilibrium conditions. And this is the so-called harmonic force constant, which will be very important later. And the harmonic approximation, as I said, truncates after the quadratic term. And since the first term here, or this term here, the linear term is 0, we end up with a term like this, which looks kind of similar to a harmonic oscillator, which is why it's called the harmonic approximation. With that, we can actually start an equation of motion. And I don't want to bore you all with too much math, but in the PDF, you will see all the math that you can do to, here are the 2 slides of math. We start with an equation of motion here. Mass times the second time derivative of your displacement is the same as the negative of your derivative of potential energy with displacement. And if you're interested, you can look it up in your PDF. I will skip those 2 slides and go to the actual solution. The solution in the end becomes an eigenvalue problem with a frequency squared times an eigenvector equals to the dynamical matrix times another eigenvector. This dynamical matrix is the central problem that we need to solve to calculate phonons. And this dynamical matrix contains a phase factor, which only depends on the difference in the supercell locations. As you can see, there's no kappa index here. It only depends on the actual supercell coordinate. we have our force constant here, and we have the masses of the two atoms. And the atomic displacements, the time-dependent atomic displacements, is essentially just a wave that depends on the eigenvector and a phase factor, Q here and the frequency here, and the position in the supercell. Not the atom itself, but the position of the supercell. The atom dependency only comes in here at the mass and the eigenvector. Looking a little closer at the dynamical matrix, we see we actually know most of what we need already. This position here, we know where the supercells are located because we know the structure. This Q is an input parameter. The masses we already know by just looking at a table of atomic masses. But this one here, the force constants, we don't know. We have to determine these force constants. How can we do that? We just need to remember how the force constant is defined. It is the second derivative of the potential energy with respect to the two atomic displacements. And if we use the central difference method for derivatives, we arrive at essentially this term here. Just applying the first derivative, we arrive at the first derivative of the potential energy with respect to a certain displacement of an atom, and we take the derivative with respect to the displacement of a second atom. And if we recall that the first derivative of the potential energy with respect to a displacement is a force, we arrive at this equation here, which means that we need the force on atom beta, or of Cartesian index beta, on an atom when another atom is displaced. Forces are something that we can calculate easily with density functional theory. So the strategy is going to be that we displace an atom, or all atoms, along a direction and calculate the force with DFT. With that, we get the force constant. And with the force constant, when we go back one slide, we get the dynamical matrix. And with the dynamical matrix, we can use an eigenvalue solver to get all the frequencies and all the eigenvectors. And with that, we know how the atoms displace in a crystal. Now we have a ton of atoms in a crystal, say 10 to the 23, 1 mole of atoms in a crystal. And we have 3 Cartesian directions. So that sounds like an incredibly big calculation we need to do, but we can do a lot of simplifications. So the strategy for a DFT calculation is to first relax the unit cell structure to get to equilibrium. The forces must be as close to 0 as possible because the equilibrium condition says forces are 0. This in practice is really only possible with cubic structures, or a lot of structures where forces zero out by symmetry. So you often have residual forces. We create a supercell structure then with displaced atoms. How big is the supercell? That really depends on the system you're looking at. You need to do a convergence test to be rigorous to get the correct supercell size. And then you calculate the forces using DFT. This is the easiest part because DFT can easily calculate forces. The only problem is sometimes you need large supercells and calculations can be really expensive. Then we determine the force constants with the forces, calculate the dynamical matrix, and solve the eigenvalue problem. Now I said we can do simplifications, and that is because we have translational invariance. It doesn't matter if I distort one atom in one cell or in the next supercell. We don't have to do any of these repeating calculations. So we only need to really worry about the atoms in the original unit cell. And as Dr. David Hicks alluded in prior talks using symmetry, we can reduce the number of distortions. So let's say we have a crystal that looks the same along the X, Y, and Z direction. We really only need to distort it into one direction and can recover the forces when we distort it into the other two directions using symmetry. Because they look the same, the result is going to be the same, except for that your axes are going to be flipped. Oh yeah, another important note about supercell size, they the atoms must not interact with their periodic images. So that is another really important condition when we use the supercell size, or when we determine the supercell size. With that, I will start a demonstration about what AFLOW does to calculate phonon frequencies. I will stop sharing for a second so I can show the video portal and also the slides, hopefully at the same time there. Can everybody see? Big enough? Or should maybe get a thumbs up or a comment if it's too small. I get a thumbs up, so it looks good. Okay, so while you're in your video portal, don't forget to module load AFLOW. I personally keep forget doing that. In your desktop, day 4, you should have a directory called 10 Phonons that contains the PDF and also contains an exercise directory. But we will actually start creating the AFLOW in file using the commands, the command AFLOW proto ACF4 225A aluminum, because that's the prototype for aluminum, and we add module equals APL. As Professor Cormac Torres showed last time, this automatically uncomments AG, for example, in this case was AGL or AEL. Here will automatically uncomment the APL calculation module. So let's go into the folder, AFLOW data aluminum, and you will see an AFLOW in file. We will make a few simplifications, and that is only to make the, that's big, only to make the calculation go faster. For now, you should never use only 1000 kbpra. This will never be enough for your calculation to really converge. So inside AFLOW-APL, make sure that this is you're changing the correct kbpra. Change kbpra to 1000, then change the minimum atoms to 100. The min atoms is used to create the supercell. We'll try to create a uniform supercell with at least 100 atoms. Then polar goes off. Just do that for now. I will explain what the polar option is later. And way below, there should be a spin option. We also turn that off. We know that aluminum is not magnetic. Now that it's zoomed in, it's of course very hard to see where the spin is. There it is. So just look for the spin and change this to off. Save it, and then we start to just run the directory with AFLOW run. So it has a bunch of output, it analyzes the symmetry. Here you see, here it starts running VASP all of a sudden. Why is it doing that? Because of the point that we have before. We need to relax the structure so the forces are minimized. So the forces are 0. Typically, what AFLOW does and what a lot of VASP calculations also do is to relax until the energy is converged. Here, we need to relax until the forces are below a certain threshold. I prefer 0.001 eVol per angstrom. This is very, very well converged. These are very well converged forces, because otherwise the condition that the equilibrium forces be 0 are not fulfilled. So while this is running, are there any questions on theory, on how to run VASP? I know I didn't go through the math to get from the equation of motion to the eigenvalue problem. But are there any questions conceptually about phonons? Appear to be the case. So the relaxations are done. As I said, it was very fast because I made the calculation very crude. And you see the supercell here, while it was still flashing up a little bit, was built as 5 by 5 by 5. It's uniform because aluminum is cubic, and 5 by 5 by 5 is 125 atoms. If it was any smaller, 4 by 4 by 4, we wouldn't get to 100 atoms. So let's look at the directory. There's a lot of different files about the relaxation. Here we see we have a concar relax underscore APL 1 and 2. That's different compared to the other AFLOW relaxations that we saw before, where it was just relax 2. And we have 3 directories. We have APL 1, 2, and 0 state. The 0 state directory is the undistorted supercells, so where no atoms are displaced, and that is important to maybe zero out any kind of residual forces that you have. It's not necessary though if you use the central difference method, which is what we're using. Then there's 2 directories here, something that says A0, D0, P, and M. P and M is because we use the central difference method. One is distorted in the positive direction, and one is the atom is also distorted in the negative direction. You can disable that. The README inside the for APL tells you exactly what the options that you have. So let's look at the file that I'm showing here in the presentation. The so-called APL fccalc state.out. This file describes kind of essentially what we've been doing. You see the supercell dimensions here is a 5 by 5 by 5 supercell. Here's the input structure, and here, let me just mark that a little bit more, is the actual distortion that was applied. You see it was distorting the atom 1 into the direction 0, 1 over square root 2, and 1 over square root 2. So it distorted it along inside the YZ plane. So the distortions don't have to be Cartesian, don't have to be along X, Y, and Z. Sometimes we actually want it to be at a higher symmetry direction, because that way our calculations become cheaper, and that's something that AFLOW does automatically. So if you're curious about what the distortions are that you got, this is the vector here that you need to look at. This is the vector, the distortion vector. Any questions about what AFLOW was doing here? So it was doing vast relaxation, 2 vast relaxations to minimize the forces. Then it created a supercell based on the number of atoms that you gave. It is possible to also define a predefine a supercell dimension. Then you use this keyword supercell equals 5x5x5. There don't appear to be any questions. So okay, so now we go to see how this actually looks like when we're done, because the next step would be to do DFT calculation on a cell that has 125 atoms, which on our video desktop we obviously cannot do, but in a cluster this is not that big of a problem. Oh yeah, what's the default value for the distortion magnitude? Our default value is 0.015. And you can tune this, I can show you, it's a very good question, with, yes, thank you, Corey, for putting that in the chat, 0.015 angstroms, and you can tune this with this parameter here, distortion magnitude, DMAG. I can also put that in the chat. DMAG was 0.015. And of course, the default value can be changed in the AFLOW-RC file. Most of these AFLOW in parameters are tunable in the AFLOW-RC file. So if you think 0.015 is not enough or it's too short, you can change it in your AFLOW-RC file and get a different default value. I think other codes, some other codes use 0.01. Some other codes, I think, use 0.02. But typically, when you're around between 0.01 and 0.02, you're good to go. As you can see, 0.015 is a very small displacement, and that's enough for phonons to get the forces. Any other questions? That's not the case, then I will move on to showing you what we can actually do with this. What can we get out of these phonon calculations with APL? And for that, I have an exercise directory where I've already done the supercell calculations. In here, you can see inside exercise, you have an aluminum directory. And I have basically filtered out all the files that we don't need. So this one here contains the QMVASP out file. It contains the forces that we calculated in the AFLOW in file. So let's start the post-processing. We'll do a bunch of readings and symmetry calculations at first. Shows that the supercell calculation is okay. And here it's starting to read the force files. And this part here can take actually quite a while. It calculates the site point group symmetry of the supercell. And that is done to symmetrize the force constant. The reason for this is because we're using a finite size of the supercell. Technically, to make this a real calculation, we would have to use an infinite supercell size. And we also have some simplifications in density functional theory. For example, using a Fourier transformation for it. And all these introduces small errors in your forces. So your the sum of your forces, for example, is not going to be fully zero, even though it should be. And you will also get some deviations from your crystal symmetry, and this is what we are doing here. We are calculating the symmetry of every single site point group. I think Dr. David Diggs talked about it earlier, and we will adjust the force constants to fulfill the symmetry of the crystal and fulfill the so-called sum rule, which requires your forces to be zero. And when we check once it's done what it did, it has a bunch of files that all start with aflow.apl. And it has some DOSCAR eigenval k-points and postcar files. They all start with pH to show that this is for phonons. And these are DOSCAR eigenval and k-point valued or formatted representations of the phonon band structure, or phonon dispersion, and the phonon DOS. So let's plot. You can do print equals PNG, or you can leave it out if you want a PDF. Out file is just the file name that you want to give it. And when you see, there should be a PDF now in that directory. Here, there it is. So let's look at that PDF. Zoom in a little bit more. So this is a combined density of states and band structure plot, as we've seen before, but this time it's not the electronic band structure, it's the phonon band structure. Now let's look at the phonon dispersion or phonon band structure here. We see that we have near the gamma point, we have one line that starts splitting apart at the X point, so it's two degenerate dispersion branches. In Phonon, we call those branches. And these are the two transversal phonon modes talking about. And they are degenerate near the gamma point for aluminum. And this one here is the one with the higher frequency is the longitudinal one. And if we start counting the branches, we see that we have no more than 3. It's always going to be 3. You will never see more than 3 lines for aluminum because we only have 1 atom in the unit cell and we have 3 degrees of freedom. That can be generalized. You will never see more than 3 times the number of atoms or number of branches you see is never more than 3 times the number of atoms. If you have more than those, something is really wrong in your calculation. Or we have a bug. But yeah, you should always see 3 times the number of atoms or branches, never more. You can't. It's physically impossible. You can also see that the frequency at gamma point here is 0, and that is not a coincidence. It has to be 0. And you also see that everything here all the frequencies here are positive. And that is not necessarily the case. I will show you at the very end what happens when the frequencies are imaginary. They are always either positive and real or imaginary. And having imaginary phonons has 2 origins. Either the compound is unstable, or there might be an artifact, and that means your phonon calculations are not properly converged, either because you don't have enough K points or because your supercell is too small. Another thing I want you to be aware of is 2 files. One is the APL Thermodynamic Properties file. They contain a few thermodynamic parameters. One is the 0-point energy, the internal energy, the vibrational free energy, the vibrational entropy, and the heat capacity, each per cell. So these thermodynamic properties can be very important for when you calculate the Gibbs free energy. So the vibrational free energy can be used as an additional term for the Gibbs free energy, and they can be very important for phase stability. There are examples out there where the vibrations actually explain a phase transition where just enthalpy didn't do the job. The other one I want you to be aware of is the displacements file. The displacement file is, these are the mean square displacements, the X, Y, and Z direction as a function of temperature. As I showed earlier, we can calculate the displacements with the eigenvectors, and these are the mean square displacements here. And as you can see, the displacements are not very big. They are, if we just take the square root of this, they are of the order of less than an angstrom, 1/10 of an angstrom, and they increase with temperature, as you would expect, because they oscillate a lot more when we turn up the heat. That I will move on to. Can everybody see the full screen, the presentation?
Yes, it's visible.
I see it slowed down. See a slowed down reaction though. Okay, which part do you want me to reiterate? I will try to slow this down a little bit more. You'll also get to do the exercises where this post-processing is going to become a lot more intuitive and a lot more hands-on. Yeah, the thermodynamic properties can also be plotted. The command here at the end, plot thermo. Out file, let's just call it aluminum. And you see there are 1, 2, 3, 4 additional files, and they yes, it is in the I think in the AconVasc README. And the APL README has all the options for plot thermal and plot pH disk DOS as well. Anything, I think most of them have the same options, except for that you can, as the GAN structure, except for that you can specify the units. It doesn't have to be terahertz, it can also be inverse centimeters and millielectron volt. But yes, the APL README, which is here, the APL README should contain all of this. It also contains the Harmonic Approximation, which we're not going to talk about because there even post-processing is extremely expensive. Since it's very big, let me output this into a file. Yeah, it's in the APL README, and all the options are in here. Ooh, square root 2. So how do we specify a 2 by 2 by 1? That is a very, very good question. You can do this in the AFLOW-RC file, and you can just add AFLOW-APL supercell 2 by 2 by 1. So it works with integers. And square root 2, this is not in AFLOW yet, but I am working on implementing non-diagonal supercells. If you have the supercell keyword in your AFLOW in file, it will ignore min atoms, so supercell takes priority. Yes, currently we only have integer values for the supercell, but we will implement non-diagonal, or I am working on implementing non-diagonal supercells for that case. Yes, for charge density waves, this is very useful. What I would recommend for square root 2 for now is to rearrange, or I'm assuming you're talking about like an hexagonal or molybdenum disulfide. I would recommend maybe putting into like the orthorhombic representation and try to get an integer or a diagonal supercell for now. Any other questions? Doesn't appear to be the case. So I will show you the output files. They're here. For example, the vibrational entropy. If this opens, there it is. The vibrational entropy increases with temperature, as it should. Entropy should increase with temperature. And here's the vibrational free energy, which decreases with temperature, and can be used, for example, to calculate reaction vibrational free energy differences. But you will get to plot these files soon in the exercise. Here again in the slides, you also get to see the phonon dispersion. We looked at it. These are the equations if you're interested on how we calculate these files. It's all based on the Phonon DOS. They're all in your PDF. I will obviously not go through them right here, but they're there if you are interested. Here are the plots for aluminum that we show. We see the vibrational free energy goes down with temperature, internal energy and entropy increase with temperature, and the heat capacity converges to 3 kV per cell, and it should also converge to like 3 kV per atom, because each branch will essentially get the Boltzmann constant heat capacity. A quick word to phonon numbers. So phonons are bosons, and they follow the Bose-Einstein distribution, and which means that it follows essentially this equation, and we see that at low frequencies, acoustic phonons dominate, or the low temperatures, acoustic phonons which have lower frequencies, they dominate, and with higher temperatures, we start exciting phonons with higher frequency. You can see the phonon numbers increase with temperature. There is no competition between the different frequencies. So with that, I know that was quite a lot. It's not an easy topic to go into, but if you run the exercise, run the post-processing, and kind of play with your output files yourselves, you will probably get a lot better handle on this calculation. So why don't we go into breakout rooms, and you can run the post-processing and actually look at the different files. I think for the next, maybe, what time is it? 10:45, maybe for the next 15 to 20 minutes, you can start running post-processing and look at the output files. The important part will be to add this tag DOS project on to the density of states, to the AFLOW-in file, because that will actually get you the atom projected phonon density of states, and we will continue with that, discussing a little bit about how the different atoms are, where the different atoms can be found in the phonon density of states. Okay, the first exercise was to look at the displacements that were calculated in the FCalc state file. You will see, for example, here for magnesium oxide, that we have two displacements. They are the same for magnesium and oxygen. They are both along the YZ coordinate here. You can see that with this vector here, these two vectors here in the distortions part of that file. And the next one was to look at the average mean square displacement. That is inside the displacements file at 300 Kelvin. And for that, you just need to scroll up or down, depending on where you're at in the file, to 300. And you see that we have the same displacements along all three coordinates because it's cubic, and that magnesium here is larger than oxygen. And there's going to be a trend that you see when we look at the values for all of them. The isochoric heat capacity can be found in the Thermodynamic Properties file. And at 300 Kelvin, you just need to look at that line as 4.54 for magnesium oxide. You can divide it by 2 to get to the number of to the property per atom. And I'm going to go ahead and present the values for all four systems. Here we have the mean square displacements. What I would like you to, or the displacements first. We see that for magnesium oxide, boron, arsenic, and iodine carbide, they're all the same. They're all along the phase diagonal. And for zinc sulfide, which is hexagonal, it goes along the body diagonal. If you plug in the vector here and kind of visualize it, you can see it goes along the body diagonal. So it's trying to find a very highly symmetric displacement, because there's a higher chance that we can actually reduce the number of K points that we need or that we calculate, and it makes the calculation cheaper. The mean square displacements, I want you to take a closer look at it. These are the values. You can always see magnesium has a slightly larger displacement than oxygen. Boron is significantly larger than arsenic. Zinc is larger, and sulfur and niobium is smaller in this case than carbon. So it appears that the lighter atom distorts much more with temperature. And that makes sense. We would expect to have a lighter atom to have larger oscillations. The last thing was the phonon dispersions, and here they are for all four compounds. You see, especially with the DOS, that magnesium portion is at a lower frequency but overlaps strongly with oxygen. For boron arsenide, boron has a much higher frequency than arsenic. Arsenic is completely in the low frequency spectrum. We even have a gap here. Zinc sulfide, we have a little bit of overlap, but overall zinc is at the lower frequencies, and sulfur is at the higher frequency. In niobium and carbon, we also have a gap. Niobium being at the lower frequency and carbon at the higher frequency. And the reason for that is primarily mass. Carbon has a much smaller mass than niobium, and same with boron and arsenide. And magnesium has a slightly larger mass than oxygen, but we see a lot of overlap because the masses are very close together. So we see that mass determines essentially where in the frequency spectrum your atoms will be. It's not necessarily 100% true because the force constants also matter, but mass is a very, very important factor, and that can be used, for example, to engineer this phonon gap here to tailor, for example, thermal conductivity, which is phonon-phonon scattering, and you can kind of play with the selection rules there a little bit. Another thing I want you to be aware of here is that rule of discontinuity at the gamma point here, and that is the next part I want to talk about, and that is polar materials. So I said polar off for aluminum, but all your calculations post-processing at the polar setting on. So why is that the case, or what is so important about polar materials? Imagine we have these oscillations, the longitudinal opticals, so they're out of phase. And here we have longitudinal, and here we have the transversals, so they go perpendicular to the propagation direction. So what happens when the atoms now move closer together here or further apart here when they do their motion? They will at some point move back because they're oscillating back and forth. But if they have different charges, there's an additional force that attracts them. So they try to go further apart, but there's an electrostatic charge that attracts them to each other. We don't see that force really change in the transversal phonon modes. We only see them in the longitudinal modes because we actually have the counteracting force here, and here they would actually just experience the same forces that drive them back in the oscillation. And that causes a split at near the gamma point. This is a long-range Coulomb interaction, and occurs at long wavelengths. Long wavelengths mean small q vectors, and the smaller your q vector, the closer you are to gamma. But it doesn't directly happen at the gamma point, only near the gamma point. And the harmonic approximation of the regular dynamic matrix does not account for that effect. And we need to apply a so-called non-analytical term correction. And that just needs to be added to the dynamical matrix. There are multiple attempts or multiple approximations to doing that. And we are using the Wang approximation. It's very easy to implement and can be calculated directly using the dynamic matrix. So with that, I want you all to check out. Let me share both the slide and the video portal. I want you all to check out the file AFLOW-APL polar.xml. You see there's two terms in here. The so-called the Born tag and the epsilon tag. I kind of skimmed over it. I should probably go back here. This epsilon tag is the dielectric tensor, and these Born charges or Born tag are these effective charges you see here. So you can see that this correction is largest when these charge tensors are large and the dielectric tensor is small. So insulating materials with high charges will have the strongest corrections here. And that's because of that additional force. So if you want to see how this looks like or how this affects the phonon dispersions, we can do the following thing. We can turn the polar corrections off. Should be here. There it is. Just change polar to off. And then just run it with a new log file. Otherwise, it will refuse to run in that directory. And you don't have to recalculate the symmetry, it just reads the force constants, and then we will get it has to rerun everything. It needs to recalculate the phonon density of states. And you can calculate the phonon dispersion. In your case, magnesium oxide, nonpolar. And you will get a new magnesium oxide phonon dispersion. And when you compare this with what we had before, you see that the optical part here is degenerate at the gamma point. But here, when you include the polar correction, it is not. And I'm going to switch back to the slides to just show you, here's magnesium oxide. We see we have a large dielectric tensor and or we have large charges and a small tensor, so we see a huge correction at the gamma point. Or an arsenide has small charges and a larger dielectric tensor, so there is a difference, there is small splitting, but you really can't see it. But it is there, it's just of the order of like a tenth of a terahertz. Zinc sulfide has large corrections. You see here we have some degeneracy and that is split here, but there's another thing that we need to keep in mind. Look at the gamma point here for the polar material. We have a discontinuity, and that is because for non-cubic systems, it even depends on the direction. So that discontinuity here is normal and to be expected for non-cubic materials. And here we see we have large charges and a small dielectric tensor. For niobium carbide, we have a huge dielectric tensor and small charges because the system is fairly metallic, and there we don't see any kind of splitting. Any questions about this phenomenon? It's very important to include these polar corrections if you do insulators and materials where you expect large charges. Doesn't appear to be any questions, so that's all fine. We looked at a bunch of dispersions, but how does that help us? What does that give us in terms of how phonons look like? We can visualize phonons because we are able to calculate the displacements. Remember, we have this is the displacement vector. We calculated the mean square displacement, and we're going to look at the x point. At a specific x point that has the coordinates half, 0, and if you do the math with these reciprocal space vectors, you get at a propagation direction of 2 pi over a in the z direction. And this one here is one of these phonons. So you can see it would propagate along the z direction, and you see that these atoms oscillate with a periodicity of two lattice lengths, and it looks like they are going kind of out of phase. They're going in phase. Look at, especially because they have a periodicity of 2, especially follow these atoms here. And this is a longitudinal acoustic phonon, because they go along this propagation direction along the z-axis. This one here is a transversal acoustic phonon, because the oxygen and the magnesium are going in phase, but they're transversal to the propagation direction. The optical phonons, look here, you see that the magnesium and the oxygen atoms are out of phase, and they're going perpendicular to the propagation direction. And this is a transversal optical phonon, and longitudinal optical phonon looks like this. We see here the magnesium is not moving very much, but you can see if you're looking close enough that they are going out of phase, and they're going along this direction, so they are a longitudinal optical phonon. It looks like I'm running a little short on time, but AFLOW is actually able to create these files, these scene files, using this command in the file excrisden. The instructions are in your PDF if you ever want to reproduce them, and you can create GIFs like the one here before using the excrisden software. Unfortunately, I don't have enough time to demonstrate this because I want to talk about something else. So let me. Yeah, the instructions are in their PDF, how to control them, how to create these GIFs. So I talked earlier about that phase stability is important. I also talked about how frequencies are positive and real or imaginary. So the entire premise of this talk was the harmonic approximation, and we're talking about equilibrium conditions. In equilibrium conditions, all displacements increase the potential energies. The forces are restorative, which means that if you're distorting your atom in one direction, it will go back to its equilibrium condition, and then will oscillate out of this equilibrium condition. It will always go back and forth. But what if we're not in equilibrium? What if we're not in equilibrium? what happens if we displace an atom and it decreases the potential energy. Then the forces are not restorative, and that leads us to a condition where omega squared is smaller than 0. And that means the frequencies become imaginary. This is how it looks like for beta titanium. It's BCC and is unstable at room temperature and at 0 Kelvin. This is hexagonal titanium, which is the ground state. And you see we have positive real frequencies. But what happens with BCC titanium? We see that we have frequencies that go below 0, which is how many plotting programs, including ours, display imaginary frequencies. And this compound is completely unstable at room temperature. We look at the minimum, the endpoint, which is 0, 0, 1/2. This corresponds to a 1 by 1 by 2 supercell. And the P point, which is a quarter, 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 that corresponds to a 4 by 4 by 4 supercell. So we will have modulations or atomic displacements along these supercells. And if you are creating these displacements with the equation that I showed you earlier, you can actually do a relaxation calculation and calculate the phonon displacements, and you will see that once you have a distorted structure, you will get real frequencies. And these displacements are necessary to stabilize the structure. Above 1100 Kelvin, 1155 Kelvin, this distorted structure is going to be stable because it distorts according to the positions of the imaginary frequencies in reciprocal space. And you can calculate those, and for example, one of y'all mentioned charge density waves is kind of the basis of charge density waves. These like instabilities are causing distortions, and you can see these instabilities in the phonon dispersions. With that, the harmonic approximation can be expanded. The quasi-harmonic approximation does phonon calculations at different volumes, and Dr. Andriy Smolyanuk is going to talk about this in a little more detail later in the next session. And we can go higher order, do higher order contributions, which are anharmonic phonons, which AFLOW can calculate using the AAPL module. This is used to calculate thermal conductivity. Thermal conductivity calculations with anharmonicity is extremely expensive. Even the post-processing step with only 4 cores that we have will take a really long time to do. That's why we're not talking about this here in this workshop. But AFLOW can do 3 phonon contributions to calculate thermal conductivity. And there's also renormalization effects of phonons, which leads us to self-consistent phonons. If you're interested in that, this is the keyword to look for. And here's a plot for carbon thermal conductivity. And you see it has a very high thermal conductivity, 2000 watts per meter Kelvin. This was calculated using our AAPL module. So AFLOW can calculate thermal conductivities as well. With that, are there any questions? If there's interest in looking at how to calculate, how to plot these GIFs, or how to get these GIFs, I'm happy to do that over the break. So yeah, any questions about what APL can do or about phonons? We don't have the modulated structures in AFLOW yet. This is something that we still need to implement, but they can be calculated. If you want to create these modulated structures, yeah, AFLOW cannot do that yet, but we are working on that in the future.
Marco, there was one question that came up in my session.
Yes.
So if you go to slide, I think it's slide 20, where you have the displacements.
Mm-hmm.
Well, okay, so the question in my session was a bit more about where these displacements come from, so I might have answered that. But if you look at the zinc sulfide, the results for zinc sulfide seem kind of counterintuitive because zinc seems to have a larger displacement than sulfur, even though zinc would be heavier than sulfur. If I'm right, if I'm reading this properly.
Let me double check, but
Yeah, okay, I don't know if you knew where that came from or if that's something.
maybe I accidentally swapped the two.
I don't think so,
Yeah.
because the question in my session was giving the same. I think it was Simone who was asking the question. I think she saw the same, similar numbers. Let's say that it was the
That's
displacement
similar
was
numbers.
different. Okay, it's something we need to look into because it is.
I'll look into it over the break, but yeah, that does seem counterintuitive that the heavier atom is having a larger displacement.
Okay, it's not just me that found this weird. Okay.
I mean, these are all this is what I was talking about also, that mass is not everything. Mass is a good indicator, but we also see that we have a lot of creeping of the zinc into the sulfur, and that is in this case is based on the force constants. Yeah, mass is not everything. This is an important take-home message too. It often helps for like niobium carbide. The mass difference is so enormous that mass really dictates everything. For an arsenide, the mass difference is so big that mass dictates everything here. But this might have a force constant problem. Something that would be interesting to see, I might do that later, is to calculate the displacements with I mean, the polar correction shouldn't matter too much. It's really more the splitting here in the optical regime. But this is very likely an effect of the force constants, which are determined by your electrostatics, the distances between the atoms. So yeah, the intuition that a larger mass has smaller displacements is often true, but not always. And that's a force constant phenomenon, which are independent of the mass of the atom. You can see this, for example, with binary carbides too, where there's not necessarily a good correlation between the mass of the cation and the actual force constants that you see, or that in the phonon frequencies that you see necessarily because of the forces, because of the force constants and not of the mass. It's a good question though. Phonons are very rarely straightforward, but they're not always straightforward. Any other questions? If I want to determine the stability of a material which is more reliable, look out for imaginary frequencies in phonon calculations, or look out for positive formation energies. Oh, that's a very interesting question. The positive formation energies are definitely faster to calculate because phonon calculations can be pretty expensive. And something to consider also is that we're talking about two different forms of stability. We're talking about I think it depends on what kind of instability you have. The instabilities with phonons that you see are displacive instabilities. So when we go back to titanium, here. This displacement here is it's going to look like BCC titanium, but the atoms are going to be off the BCC positions. So if you happen to have that exact structure, you will find a lower energy. But very often you don't even know what that displacive structure really looks like. And so phonons can be a guide to find that stable structure, if that makes sense. So let's think about a chart about a BCC titanium here. It is very unlikely that you're going to catch that 4x4x4 supercell that has the correct displacements to actually make that formation energy comparison. And that's where phonons can help you guide, find the stable structure. But after all, looking for positive formation energies is a complementary analysis when you have a distorted structure, because you found that after looking at phonon dispersions, these energies are going to be smaller than, in this case, your BCC calculation.
I think a good way to put it is that sort of both a negative formation entropy and no imaginary phonons are necessary conditions for something to be stable, but not sufficient conditions.
That's a good way to put it.
Yeah.
Very good question, though. It's certainly a very big question in research.
So yeah, but if you're trying to determine whether or not a structure is stable, definitely the first thing to do is the formation entropy, because if it's positive, that'll tell you straight away this thing is not going to form. So therefore, there's no point in doing additional calculations.
So essentially, B first, A later.
Yeah, always start with the cheapest calculation first.
That's always a good piece of advice. Any other questions?
Actually, just to follow up on that as well, so something I didn't really mention in the elastic constants yesterday, but you can also determine whether something is going to be elastically stable from the elastic constants. So there's some rules of thought. There's some rules about like some rules for elastic constants that have to be if they're positive or negative. But another thing you can do is you can check this stiffness tensor you calculate. You can check the eigenvalues of the stiffness tensor. So they're actually going to be written by AFLOW in the log file. And if any of those eigenvalues are negative, that also tells you that the material is unstable. So that's another way to check.